Hi everyone, welcome to our fourth and final lecture of the urinary system. This one is going to be a bit of a biggie. There's going to be a lot of drawing with this one. I recommend having either a large piece of paper or a piece of paper and definitely several colored pencils or pens. We're going to be drawing the countercurrent mechanism, which is the loop of Henle and everything that goes on there. So be prepared to draw quite a bit today. But as always, we're going to start out with our not really attendance questions. So go ahead and start with this and pause your video after I read through these. Where does penicillin first appear in the filtrate? How do kidneys increase blood calcium? How does Ang2 increase blood pressure? And what are aquaporins? Try to answer those. Hopefully you've done that, so let's see what the correct answers are. So let's think. Where does penicillin first appear in the filtrate? Well, penicillin is a drug that travels in the bloodstream bound to a plasma protein, so it cannot be filtered. For it to appear in the filtrate, it has to be secreted. So it is one of those that first appears in the filtrate in the PCT, the proximal convoluted tubule. Next, how do kidneys increase blood calcium? Well, they do it in two ways. One is under the control of PTH, parathyroid hormone. They increase blood calcium reabsorption at the distal convoluted tubule. And second, kidneys activate vitamin D. Remember, vitamin D was partially synthesized from cholesterol in the skin. When it was hit by ultraviolet radiation, it was then sent to the kidneys to be activated fully, and then that was sent to the small intestines, and the small intestines require vitamin D to absorb calcium from our diet. We learned that back in Bio 137. How does Ang2 increase blood pressure? It does it two ways. One was it was the most potent vasoconstrictor in our body. And second, it increased the release of aldosterone, and aldosterone causes the increase in sodium reabsorption, which pulled water along with it when ADH is present. And lastly, what are aquaporins? Aquaporins are water channels, and there are two types of aquaporins. Aquaporin type 1 are the ones that are always present. They are most abundant in the PCT and the descending limb of the loop of Henle. And there are aquaporin type 2, which are what ADH is responsible for increasing the number of, and they are primarily found in the collecting duct, but also are found in the DCT, the distal convoluted tubule. So, here we are again with our kind of visually appealing nephron, but remember, this is not what a nephron actually looks like. This is just how we draw it for ease. This is how we're going to draw it today. Here is in red our glomerulus where filtration happens. Here is Bowman's capsule where the filtrate first appears. Here is the proximal convoluted tubule, the descending limb of the loop of Henle, the ascending limb of the loop of Henle, the distal convoluted tubule, and the collecting duct. Now, we are going to be drawing the nephron today, but we are really going to be focusing on the loop of Henle and, to a lesser degree, the collecting duct. So, in a little bit, be prepared to draw a nephron. Now, here is a little bit more of a realistic view of a nephron. Here is, we can see kind of the glomerulus inside of Bowman's capsule. Here is the PCT that is a little bit more convoluted, and the loop of Henle, and a little bit of a convoluted DCT, and the collecting duct, and you can see that this one collecting duct has several nephrons attached to it. We can see one of them here, but then we can see where some other DCTs would attach. And in this one, we can see where the blood vessels that serve other nephrons are. But again, this is still a pretty basic looking nephron that doesn't do it justice. So continuing to build towards a more realistic nephron, here is our pretty realistic looking nephron. Here is our nephron. Here's Bowman's capsule with a glomerulus inside of it. Here are our very convoluted tubules. We can see that they are very twisted. And here is our loop of Henle, and we can see the entire thing is surrounded by a capillary bed. Over here, the same thing. And here is our loop of Henle. And again, we can see the entire thing is surrounded by a capillary bed. Now that we are at this point, I want to point out a little bit of a distinction that you might have noticed when you did the self-study. We have not yet talked about it in the actual lecture portion of our class. And that is a distinction between two types of nephrons. Here on the left, this is one type of nephron called a cortical nephron. And on the right, this is something called a juxtamedullary nephron. And when you look at them, they look pretty much the same. They do have all the same parts. The difference is the cortical nephron has a very short loop of Henle, and the juxtamedullary nephron has a very long loop of Henle. The cortical nephron is almost entirely within the renal cortex. The loop of Henle just barely extends into the renal medulla. The juxtamedullary nephron, the tubules of the PCT and DCT are within the renal cortex, but the loop of Henle extends very, very deep into the medulla. Now, that's going to be very important for what we draw today, which, when we draw, we're going to be drawing something again called well, I've lost my train of thought, the countercurrent mechanism, and it's going to be very important for that. The juxtamedullary nephrons are very important for that countercurrent mechanism. Now, if we look at the loop of Henle, we can see that in the cortical nephrons compared to the juxtamedullary nephrons, the capillary bed looks a little different in the two. In the cortical nephrons, the capillary bed is really just surrounded by the same capillary that surrounds the whole nephron. It's called a peritubular capillary. But in a juxtamedullary nephron, the peritubular capillary surrounds the cortical portion of the nephron, but around the loop of Henle, there is a specialized capillary called a vasa recta. And here it kind of looks like a ladder. There is one branch of capillary going down one side, a branch of the capillary coming up the other side, and then pieces of the capillary crossing across. So that's the vasa recta. You might have heard the term vasa recta. You might not remember it, but we did mention it back at the very beginning of the semester when we were in endocrine and we talked about ANP, the atrial natriuretic peptide. We'll talk about that a little later today. So today, when we draw, we are drawing the juxtamedullary nephron. Most of the nephrons in our kidneys are cortical. About 80% of our nephrons are cortical nephrons. Only about 20% of our nephrons are juxtamedullary. And even though only about 20% of our nephrons are juxtamedullary, these juxtamedullary nephrons are most responsible for water conservation. These are the ones that keep us most from becoming dehydrated. And at the end of today's drawing over the countercurrent mechanism, we are going to come back to this. Remember in our first lecture when I said it's not going to make sense when I say it, but at the end we're going to come back and talk about where that juxtaglomerular apparatus, the JGA, is right where the tubule touches up against the efferent arteriole. That's where some of the regulation of filtration takes place. Today is when we're going to come back to that. So let's talk about osmotic gradients and concentration. Before we draw this out, there is a chart in the textbook where you can see what we're going to draw out in the textbook. I don't like the way that your textbook presents it. You might like it. I think that it works a little bit better if you draw it out along with me, kind of step by step. It will make it make a little bit more sense, I think. But some terms to introduce. First, the countercurrent mechanism is a way of maximizing water conservation. It's a way of using very little energy to maximize the amount of water that your kidneys can reabsorb. It would be very, very easy to exhaust all of the ATP in your body reabsorbing water. But we actually can use little ATP to get a lot of water reabsorption by using some, it's not quite right to call it tricks, but it's kind of a neat trick the way our body does it. It plays on osmotic gradients and concentration, and we'll see that today during our drawings. But the countercurrent mechanism has two portions. There's something called the countercurrent multiplier, and that's going to be the actual loop of Henle, the tubule part. So the descending and ascending loop of Henle, and partially the collecting duct. And then there is something called the countercurrent exchanger, which is that vasa recta, that ladder-like specialized capillary. And those two things work together, again, to create and maintain osmotic gradients. And those osmotic gradients, again, maximize water reabsorption while using very, very little ATP. So, the reason that I've got this little bit of stuff down here with the rabbit and the kangaroo rat and this weird little creature over here, which is the kangaroo rat, is to give an example of the countercurrent mechanism. So, the rabbit, which has kind of the same living area as a human and thus has very similar kidneys to humans, most of their nephrons are cortical nephrons, which is what we see here. They have relatively short loops of Henle. They have some with long loops of Henle like us, and even their long loops of Henle like ours, compared to a kangaroo rat, Well, a kangaroo rat, their long loops of Henle make our long loops of Henle look short. Kangaroo rats have very long loops of Henle and very few cortical nephrons. Most of their nephrons are juxtamedullary. So most of their nephrons have very long loops of Henle, and they go much deeper into the medulla than ours do. So rabbit kidneys are very similar to ours. Kangaroo rats have very, very long loops of Henle. Why is that? Well, because kangaroo rats live in the desert. They live in very harsh environments. Rabbits, they live somewhere where it's not so much that they have an overabundance of water, but rabbits, it's not hard for them to find a source of water. When rabbits are thirsty, they can get a drink relatively easily. They're not in danger of becoming dehydrated. Kangaroo rats, on the other hand, they might not be able to find the source of water for days. So, when they find water, they're going to drink it, and then it might be a long time before they get water again. They do not want to waste the water that they have in their body by peeing it out. They want to make sure that water that's in their body does not remain in the filtrate. And they do that by having this really long loop of Henle. And during that time that the filtrate is passing through that long loop of Henle, we are reabsorbing. We are maximizing the amount of water that is being reabsorbed. And the deeper it goes into the medulla, when we do our drawing, we will see the deeper it goes into the medulla, the more water is reabsorbed. And the thing about kangaroo rats, when they urinate, their urine comes out in little crystals. And I do not mean that their urine is clear as crystal. No. What I mean is it's little crystals, solid, because they have absorbed so much water from it that it's little crystals, like sand almost, because of these really, really long loops of Henle. So let's get ready to draw the countercurrent mechanism. Go ahead and get some paper ready. I'll give you a chance to do that, and we will draw out the loop of Henle, the countercurrent mechanism, and talk all about that. So let's look to see what it is here that we've drawn. I'll give you all a chance to kind of draw this out while I'm explaining it. Feel free to please pause the recording and draw this if you don't want to listen to me talk while you're drawing. But let me talk about what I've drawn here. This is that generic nephron that we've seen several times now, and we've said that it's drawn this way so that we can easily indicate different parts of it. And I'm going to take advantage of that now. So the black thing is a nephron. Over here, this round part, this is Bowman's capsule that has the glomerulus inside. Then we have our proximal convoluted tubule, PCT. We have our descending loop of Henle, ascending loop of Henle, the DCT, and the collecting duct. Now, this could be any nephron, but we're going to talk about the juxtamedullary nephrons, because even though they only make up about 20% of our nephrons, they are responsible for most of our water conservation. So outside of the PCT, most of the water that's reabsorbed is in the loop of Henle, especially in those juxtamedullary nephrons, the ones with the really long loops of Henle. So what I've drawn in this kind of greenish brown color here, this is the osmolarity
of the interstitium. So higher up on the screen, this is the cortex. The lower down we go on the screen, it's going deeper and deeper and deeper into the medulla. And at its deepest point, juxtamedullary nephrons go so deep into the medulla that they get to about 1200. And this is in milliosmoles. So let me go ahead and put that unit on here in a few spots. Milliosmoles. So 300 milliosmoles up in the cortex, 1200 milliosmoles at its deepest point. So the higher the number, the greater the osmolarity, or the greater the concentration of the interstitium. Now, for reference, in the adequately hydrated person, so in the average healthy adult male, the osmolarity of blood plasma is also 300 milliosmoles. So with all of the electrolytes and everything that's in blood plasma, we get an osmolarity of about 300 milliosmoles. Now, what we're going to do as we draw this out together, we're going to look at what's happening at each step in each location along the nephron. And we're going to look at the effects of water reabsorption and solute reabsorption, and what does it do to the osmolarity of the filtrate. So let's look to see when we first filter the blood, the osmolarity of the filtrate inside Bowman's capsule is also 300 milliosmoles, because it is practically the exact same thing as plasma. It has some differences, but it's practically the exact same thing as plasma. Now, as we move through the proximal convoluted tubule, the PCT, we are reabsorbing water, but we're also reabsorbing solutes. So, as we move through the PCT, and when we get to the end of the PCT, the osmolarity of the filtrate is still about 300 milliosmoles. Now, it's reduced in volume quite a bit, but the concentration doesn't really change all that much because we have reabsorbed water and we have reabsorbed solutes. But we get to the end of the PCT, and then we take a turn, and now we're going to start leaving the renal cortex and go down into the renal medulla. And here it's important to think about the anatomy of each side of the loop of Henle. What are they permeable to? So as this filtrate travels down, we get to a point, and granted, I've written 300, 600, 900, 1200. It is not neatly broken up that way. It is simply a gradient. The deeper you go, it just keeps increasing. So I'm doing it in very broad steps here. We get to a point where, the way I've written it, it's 300 milliosmoles inside the loop and 600 milliosmoles outside the loop. So there is a big difference in concentration. There are more solutes outside than inside because of the concentration. And what is the loop of Henle permeable to on the descending side? Think back to our last lecture. It's permeable to water and nothing else. So even though there are more solutes out in the interstitium, there is actually, the want for those solutes to come in, but they can't, because the loop of Henle on the descending side is not permeable to solutes. The other thing that could potentially happen, and it is what happens, is those solutes out in the interstitium, they suck water towards themselves. So as we go down the loop of Henle, water is being reabsorbed. Water moves out of the loop of Henle into the interstitium, ultimately into the vasa recta to be carried away. How much water moves out? Well, until they are equal. So I'm going to write a 600 here. We keep reabsorbing water until it's the same inside and outside. And that 600 continues down. Now we see here it's 600 inside, 900 outside. Again, the solutes want to come in from high concentration to low concentration, but they can't. It's not permeable to any of those solutes. Instead, those solutes suck water out. We've reabsorbed some more water. How much? Well, until the concentration is equal. And again, that filtrate keeps moving through. We get to a point where there's 900 inside, 1200 outside, and those solutes suck water out. So the entire descending limb of the loop of Henle, as that filtrate is going down the loop of Henle, we are just continually pulling water out of the nephron into the interstitium until we get to the bottom. And now the osmolarity of the filtrate is 1200 milliosmoles, much more concentrated than it was in the beginning. That 1200 milliosmoles means we have reabsorbed a lot of water. Pardon me while I take a drink. I'm sorry if this is loud. So, that leads to a couple of problems. One, every time water is reabsorbed, it goes out here into the interstitium. And if we keep adding water to the interstitium, what's that going to do to the interstitium? It's going to dilute it until eventually the osmolarity of the interstitium is going to be 300, all the way down, even into the deepest points in the medulla. Once we are at 300, all the way down, the problem that we run into is now there is no more pulling force. There's no more way for us to reabsorb all this water, and we would quickly dehydrate. Because all of the water would just remain in the filtrate as we pass through the rest of the nephron. Let me erase that real quick. All of the water would remain, and we would just urinate a lot, and all the water would just pass straight through us. So there must be a way to keep this osmolarity constant in the interstitium. Well, there is a way to do that. Let's think. As we come back up, on the ascending side, what is it permeable to? It's permeable to solutes. Now, down low in the thin segment, it's permeable to sodium and chloride, and it's passive. Up at the top, it's permeable to sodium, chloride, and potassium, and it's active. We won't really talk too much about that. We will mention it here in just a moment. But we're permeable to solutes. So we get up to this point where it's 1200 inside and 900 outside. Well, it could try to suck the water in, but we're not permeable to water on this side. What's the alternative? Everything wants to go from an area of high concentration to an area of low concentration. So those solutes, the sodium and the chloride, are going to get sucked out. I'm going to write solutes, S-O-L. And how many solutes are going to get sucked out, or are going to move out down their concentration gradient, is more appropriate to say? Well, until we reach equilibrium. And as that filtrate moves, again, more solutes move out down their concentration gradient. Until eventually we get to the upper part where we actually expend a little bit of energy and even more solutes come out. We have to spend a little bit of ATP for that. By the time we get to the top, we're actually even less than we started with as far as osmolarity goes. We're down to about 100 milliosmoles. We'll come back to that in a moment. Let's go back and look to see what the point of all of this is. Well, over here on the water side, every time we reabsorbed water, we diluted the interstitium. But over here, every time solutes moved out down their concentration gradient, it reestablished this osmolarity. So as the solutes move out, it maintains, at this point, let's say 900. But if this remains 900, that pulls more water out, diluting it. And if we dilute it, that creates the gradient for more solutes to come out. So all over on the descending side, water is getting sucked out because of this concentration gradient. Over here, solutes are moving down their concentration gradient because water keeps diluting it. But water keeps diluting it because the solutes keep reestablishing it. The descending side drives the events of the ascending side, and the ascending side drives the events of the descending side. This is that countercurrent mechanism that we were talking about, or at least the first half of it. Everything on the descending side causes the ascending side to happen, and everything on the ascending side in turn causes everything on the descending side to happen, and it doesn't require any energy. The only energy that we use is at the very top of the ascending limb, and that's just where we overshoot and we get down to about 100 milliosmoles. So now that filtrate moves through the descending limb and down the collecting duct. But let's see what happens when we need to reabsorb even more water. Let's see what happens when aldosterone and ADH are present. Well, aldosterone tells the DCT to reabsorb more sodium, solutes. So what happens when we reabsorb more solutes? It increases this osmolarity of the interstitium. What happens if we increase the osmolarity of the interstitium? More water will get reabsorbed. And at the same time that we have ADH causing this in the DCT, aldosterone causing this in the DCT, we also have ADH adding in those aquaporins in the collecting duct. That allows water to be reabsorbed. So we've maximized water reabsorption. But that's not all. There's even more to the story, because we also reabsorb urea. We always reabsorb urea in the collecting duct, but in the presence of ADH, we reabsorb more. Why the heck would we reabsorb urea? Well, what is urea? It's a solute. As urea comes out, if ADH is present, we pull even more water out along with it because it's a solute, and solutes suck. As urea comes out, and now it's in the interstitium, what does it do? It increases the osmolarity, or the concentration of the interstitium, which pulls more water out of the loop of Henle. But urea doesn't stay out here in the interstitium. It is immediately secreted into the loop of Henle. Your book shows it happen over on this side. Really, it happens on both sides, more on the ascending side, but that's not important. Urea is being reabsorbed from the collecting duct where it pulled water with it. Urea is immediately secreted into the ascending limb of the loop of Henle. What happens when urea moves into the ascending limb of the loop of Henle? It increases the concentration of the filtrate. What happens if you increase the concentration of the filtrate? Well, that is then going to cause more solutes, sodium and chloride, to move out into the interstitium. When we move more sodium and chloride out into the interstitium, what does that do? It pulls even more water out. So everything that we've drawn is all about maximizing water reabsorption in any way possible. But this is only part of the story. We're going to add even more to it. I encourage you to listen to everything that we see on this whiteboard over and over and over, because there's going to be a lot of stuff that you could miss if you just listen one time. So let's see what else is going on. Well, when we reabsorb that water, we don't want it to just kind of hang around here in the interstitium. In reality, and I apologize that this is about to get really messy, we actually have that specialized capillary, the vasa recta, that forms almost a ladder all around this loop of Henle. And when water is reabsorbed, it's passed into the vasa recta to be carried away. Some solutes also pass in to be carried away. But we do not just leave the water to hang out there in the interstitium. It goes into the interstitium, into the vasa recta to be carried away. When the vasa recta carries that water away, and just a few of the solutes, not many, it keeps this concentration elevated, which allows more water to be reabsorbed in the descending limb. And when that water is reabsorbed in the descending limb, where does it go? Into the vasa recta to be carried away, maximizing water reabsorption. Okay, take a moment, take a breather, pause the recording, because we're going to keep this same drawing, but then we're going to switch gears. Okay, so let's see what happens if we don't really need to maximize water reabsorption. What if our blood pressure is up? If our blood pressure is up, we really don't want to reabsorb a lot of water, because that would raise our blood volume, raising our blood pressure even more. Well, previously we mentioned ANP, and we said ANP, in addition to everything that we talked about, it also works on the vasa recta. What does ANP do to the vasa recta? It causes it to become leaky. Fluid from the vasa recta actually spills out, and it spills out into the interstitium. And if we're flooding the interstitium with water, we basically wash away this gradient. And if we wash away that gradient, now there is no mechanism to pull water out. So we stop reabsorbing as much water. More water stays in the filtrate, more water remains in the filtrate, and more water leaves in the urine. So this whole setup can be used to maximize water reabsorption. It can even go higher in the presence of aldosterone and ADH, or it can be reduced in the presence of ANP.
Okay, so that was the loop of Henle, the countercurrent mechanism. I know that was a lot to take care of, to wrap your head around. But you can see now why it's easier to draw nephrons the way that we do, as opposed to this jumbled up mess. All right, so now that you've drawn all of that out and you can see what happens as fluid, as that filtrate moves through a nephron, let's go back to that regulation of filtration. Remember the autoregulation, one of the mechanisms was what was seen by the JGA, the juxtaglomerular apparatus. And we said that it was sampling the filtrate as it passed through the distal convoluted tubule right where it met the ascending limb of the loop of Henle. So it had already passed the descending limb, the ascending limb, and it got to the DCT. Well, at that point, you can see that it's already had most of the stuff reabsorbed. So that's why it's important to test the concentration at that point. And that's why it can then make a call as to, do we need to reabsorb more? Do we need to reabsorb less? And it will adjust the diameter of the afferent and efferent arteriole to allow us to filter more or less. Go back to that first lecture and watch that part again and see if it makes a little bit more sense.
Now, in both of these, your kidneys are no longer performing as much as they should. In chronic renal disease, well, chronic just means long-term. In chronic renal disease, the GFR is below 60 milliliters per minute for longer than 3 months. Remember, the normal GFR is 120 to 125 milliliters per minute, so it's about half of its normal rate. In renal failure, or kidney failure, GFR drops below 15 milliliters per minute. And when this happens, it leads to something called uremia, which literally means urine in the blood. It does not mean that urine is showing up in your blood. What it means is the parts of your blood that should have been cleansed by your kidneys and left your body in the urine are now remaining in your blood. So when this happens, typically someone is put on hemodialysis, or just dialysis is more often what it's called. And dialysis is effectively an artificial kidney. They hook it to your body, it draws your blood out, it filters your blood, and then it returns the cleansed blood back to your body. So the hemodialysis machine is really doing the same thing that your kidneys do.
So now the last path of for the semester, and there's actually going to be several of them because we have a few different options when we're talking about the kidney. Blood, when it gets to the kidney, what happens if the substance in the blood is not filtered? Maybe it was something that, maybe it was a drop of water, or maybe it was a protein, or whatever it is. It's something that was in the blood and it was just simply not filtered as it passes through the kidney. Well, this is the path of whatever that substance was as it passes through the kidney and it was not filtered. I'll leave that there for a moment, but it's, I believe, in the PowerPoint that's posted to Blackboard. The second option is, what if the path is the path of something is filtered, but then as it passes through the nephron, what if it was filtered and then it's reabsorbed? So it could be reabsorbed anywhere in the nephron, but in this example, it's filtered, but then it's reabsorbed at the proximal convoluted tubule. So this is the path of something as it gets to the glomerulus, it's filtered, and then it's reabsorbed at the proximal convoluted tubule. It gets to the peritubular capillary because it was just reabsorbed. And third, what if it just gets filtered and it becomes urine? This is the most likely option. So something in the blood and then it's going to end up in the toilet. So here it's at the aorta. Now it's going to go to the kidney. It gets to the glomerulus. It gets filtered. Now it's in the nephron. It goes through the entire nephron. If it did not get reabsorbed, now it gets into the minor calyx and major calyx, eventually to the renal pelvis. It's going to leave the kidney in the ureter, gets to the urinary bladder, travels through the urethra, and ultimately into the toilet. All right, so that is, like I said, that's the last path of for the entire semester. We have one more chapter, and really we only have one more lecture. We have two more lectures, but one more lecture that is new material, and one more lecture that is more kind of a practice case study wrap-up kind of thing. All right, so I will talk to you in the next lecture. Take care.